Hi everyone, welcome to Similarity Part 2. At this point, you should feel pretty comfortable with understanding what it means for shapes to be similar. You should know the triangle similarity shortcuts and just how to decide if two triangles are similar or if two figures are similar. We're going to talk today about a few truths about similar figures. The first four on this list are pretty general and pretty easy to understand. And then we're going to turn and look at some very specific examples of how similar triangles work in different situations. So let's just start going through these. The first one just says all circles are similar. Every circle that you look at, because there's no angles to think about, we're just looking at the radius or the diameter or one of the measurements. And so because they'd be proportional, all circles are similar. Likewise, all squares are similar because the four sides of every single square are the same, then all squares are going to be similar. They all have 490-degree angles. All equilateral triangles are similar. So just because of AA, because you have congruent angles, all equilateral triangles will be similar. And then likewise, all regular pentagons, regular hexagons, regular octagons, etc. You could go on forever. Decagons, dodecagons. If they're regular, they'll all be similar to other regular ones. So that's just a good thing to keep in mind when you're looking at different figures. Okay, this fifth one gets a little bit more specific. In a right triangle, if you draw an altitude from the right angle's vertex, so let's say we go from this angle here, and we draw an altitude, that means it's going to be perpendicular to the opposite side. When you do that, do you see how there's two triangles that are now created? We have this triangle here, and then there's also this triangle here, and then there's the original triangle that we started with, right, the ABC. So these three triangles are all similar, which is really neat to think about. All we did was sketched in or drew in an altitude, and by drawing in that altitude, all three triangles are similar, and it happens because of AA. So let's talk through this. First of all three of the triangles have a right angle. I think we can all agree on that. The first triangle had a right angle at angle C. The other two triangles, the right angle is right here where that altitude was drawn, so they each have a right angle. So there's one congruent angle. Next, let's look at the green triangle and then the original triangle. They both share angle B, right? They both have that angle. They have the exact same angle in their triangle. So because of that, that's two angles in the green triangle and the big triangle. They each have a right angle and then they share angle B. And then we look at the yellow angle or the yellow triangle and the big triangle, and each of those share angle A. So they have two angles that are the same as well. So the yellow triangle and the big triangle are similar because of AA. They each have a right angle and they each share angle A. And so if the big triangle is similar to the green triangle, and if the big triangle is similar to the yellow triangle, then the yellow and the green must also be similar because of basically the symmetric property. So anytime you draw in an altitude from that right angle's vertex, you will get three triangles that are similar. It's a really neat phenomenon that happens. Let's look at the second one. So we're going to draw an altitude in from that right angle. There it is. So the three triangles that are created, so here's one, here's two, and then the big one is our third one. Those three triangles are all similar, again, for the same reason, because of AA. All right, number 6. This one says if you have two triangles that are connected such that vertical angles are formed, basically they're connected right here. We have these vertical angles. So there's one pair of congruent angles. And if the non-intersecting sides, meaning this and this, if those two sides are parallel, then those two triangles are similar because of AA. Let's talk through why. So we already have that one pair of congruent angles in the middle there based on the vertical angles. Then, because of the parallel lines, we can look at this as a transversal. And so if those are parallel, then we have this Z getting formed here, and then we have alternate interior angles because of those parallel lines. So now we have two pairs of angles that are congruent, and that's enough to say by AA They are similar. So again, if you have two triangles connected by vertical angles, and then the sides that aren't involved in the vertical angles are parallel, then the two triangles are similar. Let's look at this picture up here. So we can see that L is parallel to M. We have the vertical angles in the middle here. So obviously angle B is the same as angle B. And then because of the lines being parallel and we have this transversal being drawn in, we have that Z, you can see that this angle is congruent to this angle. And I didn't mention this on the other one, but we could have looked the other way as well. We could have seen, well, this could be a transversal, and then there's a Z on this side, right? So we can actually get all three pairs of angles congruent. We just don't need to. But the point is, again, if you have two triangles connected here in the center by these vertical angles, and then these are parallel, then those triangles will be similar. All right, just to see it again in this final picture, we know that this is congruent by vertical angles, and you can do it either way, but if this one is my transversal, then my Z is right here, and I've got that pair of congruent angles. If they have two pairs of congruent angles, these are similar by AA. Okay, number 7. If a line is drawn inside a triangle such that it is parallel to any side, the resulting smaller triangle is similar to the original larger triangle. Let's actually just start with just any triangle. Everyone just draw a triangle. If you want to draw yours like mine, I'm just going to make a triangle like that. If we make a line inside this triangle that's parallel to any one of my sides, I'm going to make it like this. So if these are parallel, then the smaller triangle, so this triangle right here, is going to be similar to the big triangle, to this triangle here. That will happen every time. Every time you draw a line inside the triangle that's parallel. Well, why is that? Why is that happening? Again, it's just like before. We can see that we've got this angle is being shared in both triangles, right? That angle is just one of the angles in both of my triangles. And then because of the parallel lines, if this is parallel to this, and here's my transversal, now I can look at corresponding angles. This angle, let's do 2 marks, is congruent to this because they're corresponding angles. And I can do the same thing on the other side. This angle is congruent to this because they're corresponding angles based on this transversal. So because of AA, those two are similar. Let's look at our 2 pictures here. It tells us that AB is indeed parallel to EC. That means that by AA, this top triangle, or this right triangle, sorry, is similar to my big triangle because they share this angle here. And then by corresponding angles, this angle is congruent to that angle. So by AA, those 2 triangles are similar. And then in our final picture, same thing. They both share angle B. So angle B is in both of the triangles. And then if this is a transversal, this angle is congruent to this angle by corresponding angles. And so again, my big triangle is similar to my little triangle. So these are just things you've got to think about. You've got to think about when you're looking at pictures, do I have this parallel line drawn inside? Do I have 2 triangles connected by vertical angles and I have the other sides are parallel? You just have to be aware of them. Once they get in your head, you know that this exists, and then you just have to sort of think through it when you look at different pictures. Okay, this next part is sort of a continuation of what we just talked about. If you have that line inside of a triangle where it's parallel to the third side, so this BC is parallel to this one, something happens here called the side splitter theorem. It's saying that once you have those parallel lines, the line divides the two sides that it's connecting. So it's dividing these 2 sides proportionally. So let's look at the proportion I wrote down here. So AC, that proportion of that to CE. So these little parts, that ratio is the same as on this side from AB to BD. So we're not looking at parts of triangles here because CE is not part of a triangle. It's just saying that it's dividing it proportionally. So the way that it divides AC and CE up is the same ratio of the way it's going to divide AB and BD up. Let me just draw another picture to make sure this is really clear, because I want to make sure that you realize it doesn't have to be in the middle. So I'm just going to draw any triangle here. Let me do this. There we go. And then I'm going to draw a parallel line down here. So these are parallel. So what this is saying is that let's put some letters here too. If this is M, N, O, P, Q. Okay, so it's saying that the ratio of MN to NO, MN to NO is going to be the same ratio as MQ to QP. That's kind of neat. The one we did right before this, number 6, was telling us that this triangle here, this smaller one on the top, is similar to the bigger triangle on the outside. So that ratio would have told us that if I did MN to MO, this whole side, then that would be the same as MQ to MP. So those both work, right? This one is talking about because the triangles are similar, and this is just looking at the way the sides are divided, the side splitter theorem. Okay, let's look at this example number 1 here. Use the side splitter theorem to find y. So if we know that MN is parallel to AB as it is marked, then the ratio of CM to MB would be the same as the ratio of CN to NA. So let's fill this in. CM is 12, MB is Y, CN is 10, and NA is 6. Let's cross multiply. 12 times 6, that's 72. It's going to equal 10y. Divide by 10 on both sides. So y is 7.2. All right, number 2. This one is not the side splitter theorem. Well, the side splitter theorem is happening, but we don't know this length or this length, right? So we're not using the side splitter theorem to help me figure this out. We're actually going to use what we learned earlier today to figure this out. Because these are parallel, then this little triangle up here, this top one, is similar to our big triangle. But I'm going to show you a common mistake people make when they see this because they're thinking about the side splitter theorem. So this would be wrong. If you set up 6 over 10 equals x over 22, this would be wrong because 10 is not a part of a triangle, right? 6 is a part of a triangle, x is a part of a triangle, 22 is part of a triangle, but 10 is not, right? This is, if we had this side here and this side here, then we could do 6 over 10 would be this side or this part over this part. But we don't have that here. X is the bottom of our little triangle and 22 is the bottom of our big triangle, where 6 is the side of this triangle. So what's the side of the big triangle? Yeah, we need to use 16. So this would be, let's set this up better. 6 over 16 is the right way. So it's the little side to the big side, 6 over 16, and then the little side to the big side, x over 22. That's the correct way to set this one up. It's using just the fact that they're similar triangles, not the side splitter theorem. Let's go ahead and reduce this. So 2 goes into here 3 times, 2 goes into there 8 times, and then we can cross multiply. So 3 times 22, that's 66, equals 8x. I'm going to divide by 8. I can divide each of those by 2, so that gives me 33/4. And then if I want to make that a mixed number, x would be 8 and 1/4. If you left it as 33/4, that's fine too. Okay, so just be really careful with that when you're setting up your proportions, especially when you're dealing with this bottom, that these are both parts of a triangle and 6 and 10 are not. 6 and 16 are, that total sum there. Just be careful with that one. Okay, this next one is just sort of a continuation of all of that. This is the parallels proportion theorem. It's a corollary to the side splitter theorem. It's saying if you basically have 3 or more parallel lines intersected by 2 transversals, the parallel lines divide each of those transversals proportionally. So if all of these are parallel, if AD is parallel to BE and BE is parallel to CF, then the way that it's dividing these transversals is proportional. So AB to BC, that's splitting up over here, AB to BC, is the same ratio as DE to EF. That's what this one is saying. Very similar to that side splitter theorem. So let's see if we can apply that to number 3. Let's look at just this top part first. So because they're parallel, we can set up 6 is to x as 5 is to 12.5. And we can cross multiply. So 5x is going to be equal to 6 times 12.5. Let's see, 6 times 12, that's 72. 6 times 0.5 is 3, so 75. So 5x equals 75. And we divide by 5, and x is going to be 15. And then we need to find y. And so we've now looking at this bottom half of this. So x over 9, let's use a different color here. This bottom half. So we have x over 9, that's 15 over 9, is equal to 12.5 over y. I can reduce by 3 here. So divide by 3 and get 5 and 3. Let's cross multiply. So 5y equals 3 times 12.5, so that's 36. 1.5, so 37.5. And then divide by 5. And so y is 7.5. Okay, for number 4, we have these parallel sides drawn in. It's a little hard to see it, but these marks in the middle here are meant to say that those sides are parallel. They look like arrows, but they're trying to show that they're parallel. And so if we want to find x, let's look at these 4 numbers here. So x is to 30 as 15 is to 26. And I can't reduce anything, so I've got 26x equals 30 times 15, that's 450. And then we're going to divide by 26. And 450 divided by 26. That's, I have to round this one. That's about 17.3. Okay, and then to find y, let's look at this side of it. So 15 is to 26 as 16.5 is to y. And then we've got cross multiplying 15y equals 16.5 times 26, that's 429. And then divide by 15. So y equals 28.6. Okay, this next part is here because it has to do with things being proportional, but it's not about similar triangles. I want to keep that in your mind so that you don't get it mixed up. This is the angle bisector theorem. Super useful theorem. It says the bisector of an angle of a triangle divides the opposite side of the triangle into segments that are proportional to the two sides forming the bisected angle. It sounds confusing. It's not as bad as it sounds. Again, there are no similar triangles in these diagrams. So let's look at this first picture right here. When we draw this angle bisector in, again, the left and the right triangles are not similar, and they're not similar to the original. So don't get that part confused. The angle measures are not going to end up being the same. We only have one pair of congruent angles here. So once that angle bisector is drawn in, what's happening is the way that the opposite sides are being divided, so the C and D, is the same ratio as the sides. So the ratio, you could set it up a couple ways. You could say that the ratio of C to D is the same as the ratio of A to B. But you could also set it up this way, saying that if I just look at the left side, so A over C would be the same as B over D. You can do that either way. So in the picture on the right, we drew this angle bisector in. So what it's saying is, one way of doing it is that the ratio of A over B is the same as the ratio of X over Y. other way of writing it down is you could set it up and kind of look at the left side. So a over x is equal to the ratio of b over y. They're both saying the same thing in the proportion because you can tell they're the same, because if you were to cross multiply, this product is ay, you would get ay here as well. And then this product is xb, and you would get xb here as well. That's how you can tell if you have a different proportion than someone else, which is very possible, but they're saying the same thing because the cross products are the same. Okay, let's practice this one out. So number one, we have an angle bisector drawn in. I can see that because these two angles are congruent. So again, it's one of those things you have to just look for and find it in the diagram. It's not going to say, hey, use the angle bisector theorem here. So we are going to set up a proportion that tells us that these two are in a ratio, so x over 4. That's equal to the ratio of this side, which is 9 over 3. We could reduce. I'm just going to go ahead and do this one. I've got 3x equals 36. Divide by 3, so x is 12. Okay, in number 2, we have an angle bisector. Here it is. Right, this is the angle bisector. We have these two angles that are congruent. And so the ratio of whatever this side is right here, the ratio of these two is the same as the ratio of these two. The problem is we don't know what this one is right here. We know that this part is x, and we know that the whole thing is 8. So we've got to figure out what we're going to call this little section here. Let's just imagine for a second that x was 2. If x is 2 and the big part is 8, then what's left here? It'd be 6. Well, how did we get that? We did 8 minus 2. That means that we can label this side as 8 minus x. It's going to be 8 minus whatever x is. We just don't know what it is yet. Okay, so when we set up our proportion, we're going to do 7. So we're going to do this side, 7 over 8 minus x. That's going to be equal to this side, which is 5 over x. Then cross multiply. So we have 7x. It's going to equal this part, which is 5 times 8 minus x. Distribute. And sorry, it's a little crowded in here, but if I add 5x to both sides, I'm going to get 12x equals 40. Divide by 12. And x is going to equal 3 1/3. Okay, last question. We have several parts we're going to find. But if you look at this diagram, we only have a couple of measurements. We have a 6 and an 8, and that's it. And we're going to need some other numbers. So notice that the outer triangle, that BCZ triangle, is a right triangle. One of the things that should flash in your mind whenever you see a right triangle is Pythagorean theorem. So if we know the two legs of this right triangle, we can find the hypotenuse using the Pythagorean theorem. Some of you might remember one of the Pythagorean triples is 3, 4, 5. If you have two legs of 3 and 4, then the hypotenuse would be 5. Well, here this is like a multiple of that. So if the two legs are 6 and 8 instead of 3 and 4, that are just doubled, that means the hypotenuse will be 10. If you're not sure about that, you could have just done the Pythagorean theorem and figured it out and done 6 squared plus 8 squared, and you would get that the answer is 10. Now that we have that, now we also notice that we have an angle bisector here. This is an angle bisector. So we're going to use the last one that we talked about, telling us when we have an angle bisector, then the ratio of this side to this side is in the same ratio as this side to this side. Okay, so we need to figure out what we're going to call CU and what we're going to call UZ. Let's call one of them X, because we don't have a name for either one of them. If we call CU X, and if that whole side from C to Z is 8, just like last time, then we can call UZ 8 minus X. Okay, so now we're going to set up a proportion that tells us that this side, so 6 over X, is the same ratio for this side, 10 over 8 minus X. Let's cross multiply. So 6 times 8 minus X equals 10x. Distribute 48 minus 6x equals 10x. Let's get our x's all together by adding 6x to both sides. So 48 equals 16x. Divide by 16, and x is 3. So that means if this is 3 now, and 8 minus 3, this is going to be 5. So I'll put those in so we have that. So we had wanted to find BZ. We did that. That one's 10. We wanted to find CU. That one's 3. We wanted to find UZ. That one's 5. And we still don't, we have to find BU. Okay. Looking back at that triangle, let's see if I can get another color here. So this triangle is what kind of triangle? Yep, it's another right triangle. So we can do Pythagorean theorem now to find the hypotenuse because we have the other two legs. So if we do 6 squared, actually let me move this over here. If we do 6 squared plus 3 squared, we're going to get the hypotenuse squared. So 36 plus 9, and that gives me 45. And then we need the square root of 45, which is 9 and 5, so 3 radical 5. So that is BU, 3 radical 5. Okay, the last two questions is finding the area of these triangles. So I hope you remember that the area formula for a triangle is 1/2 base times height. So for BCU, the base and my height of this triangle right here would be 3 and 6. So 1/2 3 times 6. So 1/2 of 18. So the area of that one is 9. 9 square units. We don't have any units here. Okay, and then for F, we're going to find the area of BUZ, which is this one. Now you notice that we don't have the height of that triangle. We don't have an altitude anywhere in that one. But what we can find is we can find the area of the original big triangle, the BCZ, because that one has an altitude. We have this right angle right here. Let's go ahead and find that one first. So for BCZ, that's going to be 1/2 base times height, which is 1/2 of 6 times 8. So 1/2 of 48, so that's 24. And if that big area is 24, and then this triangle has an area of 9, we can subtract. So 24 minus 9 is going to give me the area of BUZ. So 24 minus 9, and that's 15. So the area of BUZ is 15.